Hello, today we have 863. All nodes distant k in binary tree. Given root of binary tree is the value of target node, and integer k returns the array of the values of all nodes that have distance k from the target node. The answer is in any order. So for this example, we have target 5 and we have k equal to distance 1, 2, we have 1, we have 7, and we have 4. 174 is 7, or 741 is our return. Okay, this is special case. If target is 1, k equals 3, there is no distance, it's empty. Number of nodes, all valid nodes unique. Target is the value of nodes in the tree. Okay. Okay, we can, first solution what I can think of, we can traverse the tree and DFS, and when we found target, we can traverse down and calculate land distance, and in this case we can pick up this 7, 4, but not 1. How we can pick up 1? Because it's 3, it doesn't have means to navigate backwards. So therefore, we can convert it into any other structure, like can we convert it into linked list? No, because 7 and 4 must be on the same distance. So for example, if we have a linked list like 7, 4 from the leaves to 6, 5, so we have a distance 2. Yeah, it's not gonna work. So another thing is to convert. We cannot convert it into array or any kind. The other thing, we can convert it into a graph. In this case, we will have convert maybe with BFS, because we need distances preserved. So we convert tree into graph, and then after that we can traverse graph and find nodes of distance k from target node. So yeah, and we added to a list and return as a list of integers. So first, let's convert tree into graph with BFS really quick. So what we're gonna do, we're gonna create like graph, and maybe as default dictionary with constructor of list. So it will be like hash set with node as a key, and all connected nodes as so it will be like root, right? And all connected, so it will be like 3, which is 5, 1, and like this. And this will be list of nodes, right? Because, and then we can find target node right away from the hash set. Okay, so let's quickly traverse. While we need for BFS, we need create queue, right? And we have to add root in here. And while queue, we will if we will get element from the queue, pop left, and then we if element has left, if there is anything on the left connected, we do GE append the left, right? And also we have, because this is a graph, so we added this connection and we have to add connection back like this. Right? Because we will have to traverse graph in both directions. The same is for, oh, and at the end we added left to the queue, and we need the same for the right. Left. Oh, it doesn't have replace into selection. Selection. Okay, nice. Okay, once again. Nah, it doesn't work. Okay, let's do it manually. Right, everything for the right the same. And after that, as a result, we will have our graph. Right, so then we traverse graph. And for traversing a graph, we also have to traverse in BFS, so it will be the same. Let's add target, and we have to add like list. Let's add node and depth. Right here we added. Okay, we added it here. Now while queue, what we have to do is we unpack value from the queue, the same pop left, but in this case we unpack element and depth, and then what we have to, we can check if depth equal whatever we have depth in, we just add, we need to declare result here, and we will return result at the end. So a result will append our node. Do we have to return node or just int? Oh yeah, we have to return int. That's weird. I thought we, okay. And so it will be element value, right? So then for so otherwise we didn't, so we reached depth here, else we didn't reach depth. What we're gonna do, we're gonna for e in graph node, which is graph e, right? For, okay, let's call it for node in graph e. What I'm gonna do, we're gonna what we're gonna do, we're gonna append to the queue append, we have to append like this, and it will be target and that +1. So because will be moving forward from our current node. The only thing, I think we have to keep track of the visited, because if we will fall into cycle, we will never go back from that, right? So let's set visited as a set with targeting it, right? It's probably not a good way to declare a set with a target. So then, in this case, we have to figure out we pop, and then we only add if it's not in visited. If n in visited and not, and only then we add it to this, and we also add the node. This is node, not target, and this is when we add append visited to I think it's add to visited, so we will not get it. Okay, let's quickly check every line. And yeah, in this case, we have complexity of n amount of nodes we have in our tree. And we created this space complexity. We don't have a limitation on space complexity. Question in real time before. What is this? Okay, so we don't have any restrictions or follow-ups, which is good. And let's check, this is good, this is good. Pop left, append. We are just appending left, here is appending right, standard BFS traversals. Now we got Q, and we put same Q. I think it's okay, doesn't matter. And we have a visited and the same braid for search, but now on a graph. So we pop up element of the graph, and standard BFS, and we check, we add value. If not visited, then okay, looks good. Let's run. Submit. Perfect. Beats 82%. Wow. Okay. Yeah. Let's see who beats me. Okay, graph. Perfect. Default dictionary is the same. Stack. Okay. What stack is doing? Oh, stack is doing DFS. Does it really matter what we do if we do BFS or DFS? I thought BFS is more correct because we have we're spreading, so we're preserving distances. But this is not about distances. This is just connection, gathering connection. So I guess stack works too. It's nice. We use for, we pop, we add. Also visited the same as set. Okay. Pretty much the same. Why it's faster? I have no idea. Okay, anything else? Okay, distant helper. Okay, what is helper is doing? Find below. Oh, this is more interesting. Okay, so he's finding below. Well, this is what I discussed at the beginning. If all nodes are below, it's fine. But how we gonna find whatever is going over the root? Root one, find below. Right, found. Okay. So it depending when he is finding it, in the right or left leaf. Okay, this is interesting. I like it. So this is the same idea. So I think he's like trying to find identify in which part of the tree, and then make decision on how to find next one. This is super fast. DFS as well. DFS. Okay. The Q. Target. While Q. Distance pop left. Not keeping visited. Not parent. What? How not parent? Where is not parent? How he get it? Oh, he assigned parent? That's interesting. DFS with a parent. Okay, this is tricky part. We don't have it in our, but in Python you can add parent to it. Okay, nice. Very nice too. Nice trick. So in Python you can just add the properties you need to the thing. Yeah, I cannot add more notes. No. Very nice. Okay, yeah, basically that's it. Yeah, this is our code. Pretty much straightforward and standard. Thank you for watching.